Okay, so here's our next problem. So again, we have a different equilibrium, a different reaction. N2O4 is in equilibrium with NO2. We're given an equilibrium constant of 0.36, and we're given our initial concentration. So in this case, again, we're at one of our extreme values. So in order to predict which direction it's going to go, it's pretty easy here because we know there is no reactant here, that the reaction is going to move toward reactants, right? Mathematically, if we were to plug this in, we would get, Q would equal NO2 squared over N2O4, right? And this would give us division by 0 or value infinity, and of course that tells me that I'm going to move toward reactants, which again we can see here just by knowing that we don't have any reactants, so we have to move that way. Okay? So once we know which direction, we know that the reactants are going to go up, the products are going to go down. So if we think about the changes here, we look at the stoichiometry, right? We have a 1 to 2. So that means N2O4 is going to go up by, we call it X. NO2 is going to go down, but it's going to go down by 2X. So that means our equilibrium concentration is going to be 0 plus X, or simply X, for N2O4. And NO2 is going to be 0.1 minus 2X. And so now we have our equilibrium expressions. So now we can jump forward and calculate our K, right? Or use K to calculate X. So we would plug this into our K expression. And so we'd end up with 0.36 for our K value, right? And it's NO2 squared. So 0.1 minus 2X squared over N2O4 over X. So now we're going to jump in and solve for X. So if we were to this out, again, we're going to have 0.36 equals 0.1 minus 2X squared over X. So we're going to solve for X. We're going to use X, plug it back in, solve for our equilibrium concentrations, and do our check. Okay, so now let's solve this problem. So we used our ice table, right? So we rewrote our reaction here with our K value. Just remember, this is our expression for K, right? NO2 squared over N2O4. So based on our ice table, we came up with a concentration of NO2 as 0.1 minus 2X squared, and N2O4 had an equilibrium concentration of X. So we're going to start off here, and we're going to proceed to solve for X. So really the only thing we can do here is, right, we can get rid of this square, right? We can distribute this, factor this, right? We can, or however you want to call it, right? We can take 0.1 minus 2X times 0.1 minus 2X. And if you do that, you end up with 0.01 minus 0.4X plus 4X squared. Now, of course, there's some algebra that goes along with that I'm not going to write all out here, but, we're taking 0.1 minus 2X times 0.1 minus 2X. So we got to do the algebra, do all of our cross multiplications, and we end up with something that looks like this, all divided by X. Now we can get rid of X over here by bringing it over to the left side, so we can get 0.3X squared, or 3X, minus this string here. Now, fortunately, what we should recognize here is that this is the setup to solve for a quadratic, right? We have we have x squared terms, we have x terms, we have numeric terms. So we're not going to be able to directly solve for x, but this is where we're going to use a quadratic. So in order to solve a quadratic, we need to set this equal to 0. So we're going to group our x terms. So we're going to end up with 4x squared, right, minus 0.76x plus 0.0100, all equals 0. So in essence, we just minus 0.3x from both sides to take this to minus 0.76x. And rearrange the order of some of these terms. So now that we have this, right, remember the quadratic, right? If you don't remember, right, they go through this in the book. So if you don't remember the quadratic equation, right, it's x equals negative b plus or minus square root of b squared minus 4ac all over 2a, where our a, b, and c are the numeric terms for our square, our x, and our simple numeric value. So a being associated with the x squared term, b being associated with the x term, and c being the simple numeric term. So we're going to plug in all of our values for our quadratic. So we end up with negative 0.76 plus or minus the square root of negative 0.76 squared minus 4 times 0.1 all over 2 times 4. Now, of course, we're going to do some simplification here. And what we should end up with is x equals 0.76, so the negatives cancel here, plus or minus all of the square root simplifies to 0.65, all divided by 8. Okay. Now, if you remember back to a quadratic, of course, we're going to end up with two possible solutions, right? One with the plus, one with the minus here. And so we're going to come up with two possible values for x. In this case, x could either be 0.176 or 0.014. Now the question is, how do we know which value of x is correct? Well, in this case, it's pretty straightforward, because if you look at, say, this term, and we were to go and try to solve for the concentration of NO2, right? So remember, that's 0.1 minus 2x, right? If you used 0.176, you would end up with a negative concentration. And we can't get a negative concentration, so that means that this must not be the correct value of x, and so it's the 0.014 that's going to be our solution for x. So we're going to take that value and we're going to calculate the concentrations here. So NO2 was 0.1 minus 2x, so we get 0.072 molar. N2O4 was simply equal to x, so that's 0.014 molar. So now we have our concentrations, and again, the last thing is to do a final check. So we're going to take these concentrations, plug them into our equilibrium expression, and see if we get the correct K value. So we got 0.072 squared, so NO2 squared, over N2O4, 0.014, and we get 0.37, which is pretty close to 0.36, so that makes me confident that we indeed solved the problem correctly here. All right, so there's a couple examples, one where we didn't have to use the quadratic, one where we had to use the quadratic, and you can see these kind of solutions. Now, in the videos that I've posted, I have other problems from other sources where different people in video have gone through and solved these problems. So there should be opportunities to see multiple examples of working through these kinds of problems. And I think sometimes the more you can see of this, the better, until you get used to really doing it. Now, I should also point out, while I'm not going to go through the example, there is one in the book where if we were given these terms in terms of pressure instead of molarity, we would go through exactly the same way, right? Instead of being concentrations, right, these would be pressures. And remember, it's unitless, so it's not really going to affect the answer. It's just we can use pressures or concentrations to solve these types of problems. So just be aware that you may see a problem where instead of giving you molarities, they give you concentrations, and you're going to solve it exactly the same way. So if you are approached with a problem where you only know the initial concentrations and the rate constant, you're going to go through 3 basic steps, right? You're going to use your ICE table to solve through, find your equilibrium concentrations in terms of a variable like x. You're going to then solve for x, right? Like we did here. Once you solve for x, you're going to plug that back into the values you got on the ICE table for your equilibrium concentrations. You're going to plug the x in and you're going to solve for the actual numeric concentrations of your reactants and products. And then finally, you're going to do a check to use those concentrations to plug them back into our equilibrium expression to see if we get the right value of K. And that'll tell us whether essentially we did our algebra correctly to come up with the right value of X. All right, so we're going to pause there. The next video, I will be talking about some other types of concentrations where we can't solve a quadratic or we can't do a simple solve for X. And so we have to use some types of approximations in order to actually solve for the equilibrium concentrations.